In this tutorial, we are going to use customized unit cell files for atomistic simulations via the software package Vampire. For most of the applications, we need to include complex systems and Hamiltonian in order to realistically model magnetic materials. These include complex crystal structures, as represented here, where basically the unit cell of the materials is formed of multiple atoms. And the properties of these atoms can be parsed directly into the codes via unit cell files. Even if the crystal structures is relatively simple, you can have a long-range exchange interaction in order to obtain the magnetic properties of the materials. The long-range exchange formed of multiple shells of interactions can be easily included into the code via this feature of unit cell files. Some spin structures, topologically stable, such as fermions, are modeled via antisymmetric interaction called Jashinsky-Morea interaction. Hence, in order to stabilize the spin structures, we can use tensorial exchange, and this can be easily input into the code via unit cell files. So Vampire is an atomistic code that allows multi-scale modeling. Hence, if you have already parameterized your material from ab initio, you can include all the details from the ab initio simulations into the atomistic one via the unit cell file. So in this tutorial, I'm going to show you a simple example of a unit cell file and how can you use it in Vampire. In the next tutorial, we are going to focus on how to include tensorial exchange in a unit cell file and how to generate complex spin structures such as fermions. Okay, let's start using a simple UCF file. So if you go into the folder we've downloaded from GitHub and do a list, we see that there is already an example of UCF file called simplecubic.ucf. So let's open this via your favorite text editor, mine is Vim, and we can have a look on the unit cell file properties. So the first line is represented by the size of the unit cell in XYZ direction, and this size is basically in angstrom. The next three lines are related to the translation directions of your unit cell. But for parallelization reasons, in Vampire so far, only perpendicular directions such as here are included. Part of the unit cell is related to how many atoms your unit cell include, which is this integer here, and then where these atoms are positioned. This is an example for a simple cubic unit cell file. Hence, in order to reproduce the symmetry of this file, we can use just a single atom, as described in this picture here. And we can place this atom in the middle of the system, so we have 0, 5, 0, 5, 0, 5 position. So the first index here is basically just an ID of the atom, and this is an integer. So in our case, we called our atom 0. Then these are the positions in X, Y, Z. These are normalized to the unit cell size, so all these positions will be between 0 and 1. And then the next three numbers are related to the material. So for simplicity, we have chosen just a single material, and we labeled this 0. And then in the material file, we can specify other properties for this material, such as anisotropy or magnetic moment and so on. And the other two parameters are related to the category, but this is a more advanced feature of the code. The next part of the unit cell is related to the interaction list. In order to create the neighbor list, we need to take our unit cell and translate it in all directions. In this way, we can construct a supercell, and based on the supercell, we can calculate the interaction within our system. So the first number here is the total number of interactions within this supercell. And for a simple cubic crystal structures having just nearest neighbor exchange, we have 6 nearest neighbors interactions, 4 in plane and 2 out of plane. The next number here is related to the type of exchange interaction. So here you can add different type of exchange interactions. For the moment I'm going to add an isotropic exchange interaction. However, you can also have tensorial exchange or vectorial, where you can basically input more complicated information related to your exchange interaction. The next part of the unit cell basically lists all the interactions within this supercell. So the first column is related to the index of the interaction, so it will go from 0 to number of interactions minus 1. Then we start to specify to the code which atom interacts with which atom. So in this diagram I've shown that atom 0 interacts with atom 0 from this supercell. Hence we write this down into the unit cell file. And then you also need to specify the relative distance between these atoms. Relative distance is written with respect to the unit cell. So you specify that the atom from the unit cell interacts with the atom from the supercell that is positioned in the right of the unit cell. So it is displaced by 1, 0, 0. So this is X direction, Y direction, Z direction, and all these numbers are related to the relative position of the unit cell. The next number here is actually the exchange energy, which is joule per link. I'm going to decrease this a bit in order to modify the Curie temperature and have lower Curie temperature of the system for faster simulations. So for simple structures, it's quite easy to construct this neighbor list. However, if you have a more complicated system, then you basically need some sort of external code that will automatically generate all these interactions. As well, here you can easily put all the data that ab initio simulation can offer you. So here you can include different shells of neighbors of interactions calculated from ab initio and so on. So let's close this file. Now let's go into the input file and see what changes we need to do there. So at the moment the input file reads just the material file. However, we can specify here material unit cell file and then specify the name of the unit cell file. Okay, so now the code will read all the properties from this specific material. So properties such as unit cell size will be overwritten by whatever is written here in this file. Hence, we can delete this part or comment it. I'm going to comment this part here. To do a simple test, I'm going to decrease a bit the size of the system. So I'm going to put 3.54 nanometers here and here. So now we have a system of 10 by 10 by 10 atoms, so in total 1000 atoms. And also I'm going to add the periodicity. So I'm going to specify create periodic boundaries X, then copy these. I'm going to make the system periodic in all 3 directions. Oops, sorry. Y, Z. Okay. To do a simple test, what I'm going to do is to run a magnetization versus temperature simulation. So here will be Curie temperature, here will be Monte Carlo. I hope you've been through the previous tutorial in which is explained how Curie temperature simulation works. Then we need a couple of simulation parameters. So we need a minimum temperature, let's start with 0, maximum temperature, oops, let's put something like 160. Then we need to specify temperature increment. And then for the statistics, we need some equilibration time steps. Let's put 5,000. This is not too much. It's quite a small equilibration time step, but I'm doing this just to have a very fast test. And then we need some time step over which we are going to do the average of the property. So this is for statistics. Loop time steps, again 5,000. This is quite a small number, so you'll need to, for each individual system we're going to simulate, you need to do some very fast tests in which to see if your system is equilibrated long enough or not for these numbers here. And then we want to output the temperature and the average magnetization. So mean magnetization length. And we do the same to output this on the screen. Okay, so here we also see that there are some parameters set up in the material file. So let's save this, WQ, and go into the material file. So we have here dumping, we don't need it now, that's for LLG simulation. Exchange matrix, this number will be read from the unit cell file. So whatever you write here, it will be overwritten by the unit cell file if you specify a unit cell file. And then you need spin moment and anisotropy, so that's fine. Okay, oops, sorry. So now we have everything set up. Let's run the simulation. So I'm going to run a serial simulation for 1000 atoms, and we see here the temperature and the mean magnetization. So I set up the temperature up to 150 Kelvin. In the meantime, we can open a terminal in order to plot the results. So the results will be in output. We can plot it via your favorite plotting tool. I like gnuplot, so I'm going to open this. And we say plot output using column 1 and column 2 with line points. And we see almost our simulation is almost finished. We have a nice magnetization versus temperature curve. The Curie temperature is quite low. That's because I artificially decreased the exchange. So that's it basically.